Hello, everyone. Welcome to our presentation for the project for the class of 18645 for Carnegie Mellon University. In this project, we'll talk about a fast kernel for a Gaussian mixture model, presented to you by Chengliang Zhang, Jiajun Wang, and Yihan Liu. So let me give you a brief introduction. What is a Gaussian mixture model? A Gaussian mixture model is basically a type of unsupervised learning model within the machine learning algorithm. And there are several modes we can do to implement different types of GMM known as a Gaussian mixture model, which goes, we have spherical, diagonal, tied, or four. In this project, we'll be focused on the most common seen GMM model, which is spherical. And then why are we doing the GMM model? There are several advantages. The biggest one being that the accuracy of the GMM surpasses the accuracy of the k-means and other unsupervised learning models, as we've seen on the right side in modeling the original data. And below is basically a 3D representation of different types of Gaussian distributions forming a GMM models in the end. And these are the two graphs that generate by two different dimensions using our data set by running the sequential C code in Python and running in Python. So for our kernel design, we're actually designing kernel for the inference, which is the prediction stage within the sklearn python gmm.py function. And the specific function we are designing kernels for are the estimate log Gaussian problems, which basically outputs each data point's probabilities that belongs on each types of the clusters. And to divide and conquer this function, we actually designed four different kernels. Kernel 1 being the matrix multiply, but specifically with the column packing. And kernel 2, which is the matrix row-wise inner product. Kernel 3, vector outer product, and kernel 4, which is the summation of all matrix and vectors. So without further ado, let me bring you to kernel 1. So kernel 1 is nothing more than just a matrix multiply. So what we do is we're taking the input size matrix A with the size of number of samples. In this case, we're taking the range from 3,000 samples to as large as 300,000 samples, and times number of features. In this case, we have 4 features within the first matrix A. And the matrix B takes the form of number of samples times number of components, which is how many clusters we're doing with the Gaussian mixture model, as previously in C as 3. So the main key about this implementation is that we have to pack not in the row major order, but the column major order. The reason we're doing this is the row major order will bring out one crucial point, as we can see is the red dots over here. That's what additional factors cannot be mapped within the result. So as a result, we're actually packing everything in the column major order, and then we're broadcasting one single element for the B matrix. And then hopefully we're looking for the optimal result. As a result, we're using 9 output registers, 3 broadcasting registers, and 3 input registers. As a total of 15 registers out of the 16 registers available. Our theoretical peak is 16 flops per cycle. With that being said, I'll transfer you to kernel 2, represented you by Jiajun Wang.
Okay, so the second kernel calculates the row-wise inner product of input matrix X. That is, we take one row from the input matrix X and compute the inner product of this row vector and store the inner product in the same row. The shape of the input X is 300,000 by 4, and the output is a column vector of shape 3,000 by 1. This is a more clear grid view showing the first row of the input matrix X and the output vector. In order to fully parallelize, we read input matrix X in column major order. Because the calculation of each row is independent, the size of the kernel will be 32 by 1. We load 32 rows of input matrix X for one column into the kernel. That will be 8 SIMD registers. And we must use 8 temporary registers to store the temporary values calculated by the SIMD FMA. Thus, we use the whole 16 registers provided. After loading into the registers, we then perform SIMD FMA to compute the values. After 4 iterations along the 4 columns, we store the values in the end. And then we move on to the next 32 rows.
In the third kernel, what we should do is to complete a vector outer product. Since the vector precession is a 3-element vector, it does not fit in one SIMD register simply. To avoid wasting padding, we decide to broadcast it into 3 SIMD registers and multiply it with vector Einstein sum. By doing multiplications between these vector pairs, we can get 3 column major order matrices. After each iteration, we go downward through the vector Einstein sum for 12 elements. Considering the limit of registers num and latency of SIMD multiplication, each iteration in the kernel contains 9 independent SIMD multiplications, which will use 3 registers for vector precision, 3 registers for vector Einstein sum, and 9 registers for storing the result. It will fulfill the pipeline and does not use up logistic SIMD registers. As a result, the performance of this outer product kernel is about 30 times faster than Orange Python. And the last kernel will be explained by Jiajun.
The final kernel is the matrix and vector addition. As you can see, we add matrix A, B, and vector C together. What actually is done is that we first broadcast the row vector C into multiple rows to form a matrix that matches the shape of matrix A and B, so that we can do the final addition altogether. In order to fully parallelize, we read input matrix X and B in column major order, 24 values for each into 6 registers for each, consuming a total of 12 input registers. 8 rows are read in the kernel, giving a size of 8 by 3. Then we broadcast the 3 values in row vector C into 3 registers, giving a total of 15 registers. And then we do SIMD add of A and B, and then store it in A. And then we do another SIMD add with A and C and store it into A. Finally, we store the values of the 6 input registers A into the output matrix.
So this graph actually give you like the result overview of what's the goal actually be able to achieve by the end of our implementation after the fully implementation of SIMD instructions. So just give you a recap. Our first kernel was a matrix multiplied with a column major. Our second kernel was the matrix row-wise inner product. And our third kernel was the vector outer product. And the fourth kernel is basically the summation of different matrices for the 3 kernels we completed above. As a result, our first kernel will be able to achieve about 14.52 times faster than the original Python implementation. For our second kernel, which is actually the one with the highest performance, we'll be able to implement the code 49 times faster than the Python implementation. And for our third implementation of the SIMD, we'll actually be able to achieve 31.37 times faster. And our kernel 4 is about 22.34 times faster than the original Python implementation. With that being said, I would like to conclude that even though there are more chances and more boundaries we can push towards our theoretical peak and everything, we can conclude that our project has come to a success in the end. With that being said, I want to thank you to come to our presentation and hope you have a nice rest of your day.